Okay, so good afternoon, everyone. Welcome to this thesis presentation by Vince Cangco. He will be presenting his undergraduate thesis, the title of which he will inform us later. We are joined by our thesis panel. The reader is Professor Aladdin Hasmin, and the examiner is Professor Christian Crisostomo. So, Vince, whenever you're ready.
Okay, so before I start my presentation, I would first like to acknowledge the presence of everyone who have attended this event, to my thesis advisor, Dr. Ian Jasper Agulo, to my thesis reader, Dr. Aladdin Hasmin, and to my thesis examiner, Dr. Christian Crisostomo, as well as the audience that are watching right now. So, I greet you all a pleasant afternoon. Okay, my name is Vince Cangco. I'm a BS Physics student, and the title of my thesis is called Detecting Western Pacific Cyclones Using Convolutional Neural Network. So, to give a bit of a background for my study, if you are living in this country, the Philippines, you know that we are frequently visited by numerous typhoons every year. In fact, an average of around 20 tropical cyclones visited the Philippine area of responsibility annually. And since the late 1970s, it is reported that typhoons have intensified. This has caused massive damage in our agriculture, in our infrastructure, as well as many other industries. And it has claimed the lives of many Filipino people. This is why the weather agency, such as PAG-ASA, are closely monitoring the development of these tropical cyclones using satellites. So, there are also many methods that are developed that use satellite-based approach in weather forecasting. The first one is the LaJoy and Nichols technique. It uses the satellite images of tropical cyclones, and interpret their movement as well as the presence of other surrounding clouds to predict the track of the tropical cyclones. The next is the Martin-Holland technique. It integrates infrared data obtained from satellite images as well as other numerical techniques to estimate the wind intensity and the track of tropical cyclones. And lastly, the Dvorak technique. This will be the technique that will be highlighted in this study, where they use the patterns of tropical cyclones in its various stages. So, why machine learning? Lately, the application of machine learning is rising in popularity. So we can see this in other fields such as medicine, where they detect the presence of tumors. In education, if you know ChatGPT. But in meteorology, it is mainly used in weather forecasting, such as tropical cyclone track prediction or rain rate forecast. There are limited studies on satellite-based imagery approach. So, the machine learning model or the deep learning model that we will use in this study is a type of convolutional neural networks. Convolutional neural networks are typically used in image detection, classification, segmentation, as well as in image identification. So, it uses an image as an input, and it is processed in its various hidden layers, and it will try to learn the features. In this case, in this example, it will try to learn the features of a bird, and then it will try to identify this from a set of classes such as dog, a bird, or a cat. So in this case, the input is a bird, and it will try to output its correct class called the bird. Now, in this study, we will try to answer the question, is it possible to develop a tropical cyclone detector and identify their wind intensity using the Dvorak technique cloud pattern as its basis? And these are the scope and limitation in this study. First, in the tropical cyclones, we will only use the tropical cyclones that originate in the northern hemisphere of Western Pacific Basin. I will not be including cyclone-related pre- and post-classifications such as low-pressure areas and extratropical cyclones. So the second, the CNN used is pre-built instead of creating one from scratch. And last, the study is focused on detection of tropical cyclones in the image, not prediction of its development. As for the objectives in the study, first we will try to develop or use existing machine learning models for tropical cyclone detection. Second, show that the trained model can learn tropical cyclone features. And last, so that we might provide an additional tool to improve tropical cyclone monitoring and observation. To provide additional background about tropical cyclones, this is an illustration of a life cycle of a tropical cyclones originating from the North Atlantic Basin. So a potential tropical cyclones will start as a tropical disturbance. So it will get its energy from the sun as well as the warm ocean waters. So if the conditions are favorable, the wind intensity of that tropical disturbance will increase, and various atmospheric and geological phenomena such as the Coriolis effect will make the clouds rotate around a center. And at days 5 to 6, it will become a tropical depression. If the conditions are further favorable, it will continue to intensify, and the rotation will become a defined vortex until it becomes a typhoon or a hurricane. But if a tropical cyclone moves inland, its energy source will be cut off, so it will start to weaken and dissipate. Or if it moves further in latitude, it will transition into an extratropical cyclones. Extratropical cyclones are related to tropical cyclones, but they are weaker since the water in higher latitudes is colder, and the amount of solar energy received there is less. Now that we know how tropical cyclones develop, we will now discuss how the Dvorak technique take advantage of the fact that the various stages of a tropical cyclones have different patterns. So in the Dvorak technique, it mainly divided the tropical cyclones into 3 intensity group categories. First are the pre-storms. These are low intensity tropical cyclones. Next are the tropical storms. These are moderate intensity tropical cyclones. And last are the hurricane or the typhoon pattern type. These are the high intensity storms. So aside from their wind intensity, they are divided further into their distinct patterns. For this study, we will discuss the curved band and the shear pattern type. The second curved band is only visible in the enhanced infrared images. These are the type of images you see when someone from PAG-ASA is reporting the weather. So if you see those maps with colors red, green, or yellow, those are enhanced infrared images. The next is the central dense overcast pattern type. Is only visible in the visible range. So for the curved band pattern, the shape of the tropical cyclones is symmetrical around its center, while the shear pattern type is asymmetrical around its center, and usually the center of a shear pattern type is exposed. But at high intensity, shear pattern type disappears because typhoons have enough strength to maintain the symmetry around their center. So all typhoons are curved band pattern type. Now that we know the Dvorak technique, we will now discuss some of the studies that use satellite-based imagery approach in their machine learning models. They are mainly categorized into 2. These are the tropical cyclone classification models or tropical cyclone detection models. For the tropical cyclone classification models, they try to estimate or categorize some of the tropical cyclones. So this one is a study from Pradhan et al. From 2018. They use CNN to categorize tropical cyclones according to Saffir-Simpson hurricane wind scale. This is a tropical cyclone intensity scale used by the weather agency in US. So it has categories such as first the no cyclone category, next are the tropical depressions, next is the tropical storms, and the fourth and the eighth intensity category are the hurricane 1 to 5 categories, with 5 as the highest. So in this study, they achieve an average F1 score of 0.8 and an RMS intensity error of 18.85 km per hour or 21.04 km per hour. So the estimate of their category is within this range. Next is a study from Chen et al. For this one, they used tropical cyclone images augmented with GridSat with their satellite infrared brightness temperature and microwave rain rate data. So for this study, their input are augmented or enhanced infrared images, and their output is an estimate of the wind intensity of that tropical cyclone. So they achieve an RMS intensity difference of 15.54 km per hour. And lastly, for the tropical cyclone classification models, is a study from Combinido et al. This is similar from the study of Chen et al., but they use grayscale images instead of augmented or enhanced infrared images. And their CNN model is called VGG19, that is pre-trained on a dataset of ImageNet. So they achieve an RMS intensity error of 24.5 km per hour. So their study looks like this. They input tropical cyclones, and this is the ground truth label for that. So for example, Typhoon Haima has a wind intensity of 105 knots. This is its actual wind intensity, and their model will estimated that this image of a tropical cyclone have a 102 knots wind intensity. So this estimate is pretty close from the original. However, there are also some samples that have far enough intensity in their estimate. Next are tropical detection models. This differs from tropical cyclone classification models. It's such that the model might try to detect the presence of a tropical cyclone. It may or may not try to identify its wind intensity. However, so far the models that I have encountered only want to locate or detect the presence of a tropical cyclone. So for the study of Comner-Bonfanti in 2020, they used UNet to perform image segmentation on satellite images of tropical cyclones and extratropical cyclones from Global Forecast System and the GOES satellite series. So they achieve an IOU score range of 0.51 to 0.76. So IOU is an intersection over union. It is the amount on how much the ground truth overlap with the predicted bounding boxes in their model. Next are the studies of Tong et al. And Galea et al. They are similar in that they develop models that detect the presence of a tropical cyclone in an image. However, unlike the study of Comner-Bonfanti, it only detects or it only outputs if there are a tropical cyclone or not in this model. They did not try to locate the tropical cyclone in the image. They achieve an identification accuracy of 96% and 85% respectively. Now that we have sufficient backgrounds on classification and detection models, we will now move on the methodology of my study. In this section, we will discuss the data set that is used as well as the CNN models that are trained in this study. First, the data set. The tropical cyclone images are Himawari 8 satellite images in the infrared band of 249 tropical cyclones from 2015 to 2023. They are divided into classes according to the Dvorak technique cloud pattern. These are the pre-storm type that have a wind intensity less than or equal to 63 km per hour. Tropical storm type that have a range of wind intensity of 64 to 118 km per hour. And typhoon pattern types that have a wind intensity greater than 118 km per hour. We use MATLAB to label the images. And the data set is grouped into two, the classification data set and the detection data set. So there will be, we will split the task of the machine learning models into two. First is the classification of tropical cyclones. So we will classify them into pre-storms, tropical storms, and typhoons. And the detection data set where we will try to locate its location in the image. So this figure shows the part of the Western Pacific Basin that concerns the study. So the area ranged from 0 to 50 degrees north and from 100 degrees east to 180 degrees east. And now, detailing the data set for the classification task. These are satellite images captured at 10-minute interval of 233 tropical cyclones from 2015 to 2022. They are split into training, validation, and test set by year in roughly 50 to 25 to 25 ratio. So in training set, we will have 126 tropical cyclones. In the validation set, we will have 54 tropical cyclones. And in the test set, we will have a 53 tropical cyclones. And this table summarizes the number of images that are present in the classification data set. So in total, we will have 184,199 images that are split into their cyclone category of pre-storms, tropical storms, and typhoon pattern types. And for this one, these are sample images of the classification data set. These are infrared images of Typhoon Bangkut in its various pattern type category. The first image is a pre-storm. The second image is a tropical storm. And the last image is Typhoon Bangkut as a typhoon pattern type category. Now, after the classification data set, we will now detail the detection data set. So this one, these are satellite images captured at 3-hour interval of 69 tropical cyclones from 2021 to 2023. And it encompasses the whole area that concerns the Western Pacific Basin in our study. The training and the validation set is made up of 53 tropical cyclones from 2021 to 2022 in an 85 to 15 split ratio. And the entire test set is made up of 16 tropical cyclones in the whole year of 2023. And this table summarizes the number of images in the detection data set. There are a total of 3,169 images, 2,078 of which are in training set, 358 are in validation, and 733 are in test set. And this is a sample infrared image for the detection data set. There are a tropical cyclone present here. This one in magenta is a pre-storm type, and the one in cyan is a typhoon pattern type. And now, moving on with the CNN model that we will use in this study, we will have one for the classification task and the other for the detection task. For the classification task, its job is to classify the tropical cyclones in the training set. into a pre-storm, tropical storm, and typhoon pattern type. And the CNN model that we use in this study is called GoogleNet. GoogleNet is a type of CNN that is commonly used in image classification and image identification tasks. So it is chosen in this study because first, GoogleNet is publicly available. So its trained and untrained version is available online. Second, its performance is already proven as it won an image classification competition back in 2014. And lastly, the GoogleNet is designed with efficiency in mind so that it can be run even on modest devices. Especially as a student, I do not have an access to very strong computer. And this figure shows the architecture of the GoogleNet. And now, for its training option, the image of the input image size is 224 by 224 pixels. The test set, the images in the test set have a random rotation from 0 degrees to 270 degrees. And the algorithm or the solver used is the stochastic gradient descent with momentum with mini batch size of 128 images. The initial learning rate for this for the training in this CNN model is 0.01. That decays by a factor of 0.1 every 5 epochs. And now, proceeding with the detection task. The CNN model that we use here is called the faster region-based convolutional neural network, or faster RCNN for short. This one is from a modified GoogleNet architecture. This GoogleNet is already trained in the tropical cyclone images that we have in the classification data set. So it will carry over the weights and biases, or the things that the classification CNN model that already learned. So faster RCNN detector works by proposing many bounding boxes. So for example, in the training images, it will try to propose numerous bounding boxes. And whoever have the highest overlap range according to the settings in the training options, it will eliminate those that does not meet the criteria. This is how faster RCNN detector locates the target image. So for this one, if there is enough overlap in the ground truth label in the test set, it will retain those bounding boxes. So when it is detecting tropical cyclones, it can approximate its location. So for its training options, the input image size is bigger than the first model. It is 1024 by 560 pixels. The algorithm or the solver used is also the stochastic gradient descent with momentum. The mini batch is significantly lower for this one. It is only one image per iteration, and the learning rate is only flat 0.01. And as mentioned, the allowed overlap range between the ground truth label and the predicted bounding box label, for positive overlap range, it is 0.6 to 1. And for the negative overlap range, it is from 0 to 0.3. And now, to evaluate the performance of the machine learning models, for the classification task, we will use confusion matrix and gradient weighted class activation mapping, or GradCam, to visually evaluate the model. The confusion matrix will represent the matrix will visually represent the testing result of the machine learning model, while the GradCam technique will let us visualize on how the machine learning model looks for the tropical cyclone features. Next, the precision, recall, and the F1 score will be used to do quantitative evaluation of the model. The precision the precision measures on how much the positive class that the model predicted are correct, while the recall will measure on how much the true class samples present in the data are correctly identified. And while the F1 score is the harmonic mean between the precision and the recall. So if you have a high precision but low recall, the F1 score evaluation will be low. If the recall is high and the precision is low, the F1 score will also be low. So to evaluate that the machine learning model has a good performance, it needs to have a high precision and a high recall. And for the detection task, the performance metrics considered in this is if there are 50% or more intersection over union between the ground truth and the predicted bounding boxes, it will be considered a true positive. While to quantitatively evaluate the model, the precision recall curve is used to present the detection results, and the average precision and the mean average precision are used to do quantitative evaluation. So average precision is obtained by by getting the area under the curve of precision recall curve. While the mean average precision are just the mean between the average precision across all classes. And now, proceeding in the next section, this is the results from the training and the testing of the two machine learning models. First, for the tropical cyclone classification results, this figure shows the accuracy and the loss plots in the training process of the CNN model. So if we will notice, at around 5,000 iteration, the training plots starts to plateau. And at around 9,000 iteration, we stop the training because we see no significant improvement in its training. So in summary, the training results of the CNN model, the training duration lasted for about 30 hours, with the training accuracy at 77.34% and the validation accuracy of 75.06%. The training loss is 0.5 and the validation loss is 0.545. Now, after training the model, we now run this on our test sets. So first is the confusion matrix of the primary classification result. This one is expressed in terms of number of images. So there are a total of 40,031 images in our test set. And the next confusion matrix is expressed in terms of percentage from the total number of images. So immediately we will notice that the number of correctly classified tropical cyclones are greater than the incorrectly classified tropical cyclones. There are around approximately 70% correctly classified tropical cyclones. However, we will immediately notice that on tropical storms, there are many tropical storms that are misidentified as a pre-storms. But on other classes, the classification results are good. And now, to visualize on what features that the machine learning model looks on the image, this is called the GradCam technique. So it represents the activations in the neurons of the machine learning model and represent them as a heat map. So the blues, or the color blue, are the low activation region, while the reds are the high activation regions in the image. So essentially, the reds are the main features that the machine learning model looks for that particular class. And these images, this one, for this row, these are curve band pattern type for pre-storms. These are all correctly classified pre-storms. And the bottom rows are shear pattern type for pre-storms. So for the first one, actually for all of them, the machine learning model does not directly look on the tropical cyclones, and instead it activates mainly on the background of the images. So it's the feature that it tries to identify when looking for a pre-storm is the background instead of the cloud bands that are present in the tropical cyclones. So for the curve bands, it's usually around or across those images, while for the shear pattern type, it mainly dwells on the edges of the tropical cyclone vortex. And now, for the tropical storms, immediately we will now notice an improvement on the feature, on the heat maps of the images. So for the top rows are curve band pattern types of tropical storms, and the bottom rows are shear pattern type in in tropical storms. So for the curve band, it is now the machine learning model or the trained CNN model is now looking directly at the tropical cyclones. But for the shear pattern types, it is now it is looking directly at the tropical cyclone. However, there is a tendency to look around the edge of the vortex, just like the shear pattern type in the pre-storms in the previous figure. And now, class, for the correct classifications, we have the typhoons. So the first one are the minimal typhoons, or the lower end of intensity in the typhoons, while these are the strong typhoons. So minimal typhoons may or may not have an eye present in their center, while the strong typhoons almost always have an eye in their center. And immediately looking at their heat maps, the activation is concentrated around the center of the tropical cyclones. So for this one, the trained CNN model is now looking directly at the center of the typhoon. And now, we have discussed the correctly classified images of tropical cyclones previously. And now we will address the misclassifications. So for this one, these are pre-storm images with incorrect classifications, with A, B, and C misclassified as tropical storms, and D and E misclassified as typhoons. So for this one, immediately we will notice, looking at their heat map, that they resemble the ones from those in the tropical storms in the correctly classified heat maps. And for this one, although the images of the tropical cyclones themselves resemble those of the typhoon, the possible explanation for this might be these are tropical storms that are now weakening, that have weakened into pre-storms, or pre-storms that are now nearing their intensity into tropical storms. And also, according to the manual in the Dvorak technique, sometimes weaker systems such as pre-storms appear stronger than they actually are because of their patterns. So for this one, we have a clear background and a clear vortex in this image. And it misclassified it into a typhoon. Because if you are looking at it in isolation without the context of the map, since this cyclone is very small, and this is the outline of the Mindanao, this cyclone is pretty small. If you are looking at it as a human, if you are looking at it in the big picture, you will know that although it looks like a typhoon, it cannot possibly be a typhoon because it is smaller than the usual typhoons. However, their pattern resemble those of tropical storms or typhoon. And now, the second misclassifications. These are tropical storm images that have incorrect classifications, A, B, and C, are misclassified into pre-storms, while D, E, and F are misclassified as typhoons. So again, looking at their heat maps, we will immediately notice that since the CNN model is looking at the background, the heat map resembles those of the pre-storms. So and for the bottom rows, they resemble those of the typhoons. A possible explanation for their misclassification is that this might be tropical storms that are starting to weaken. For example, when they meet a land, they start to weaken, and sometimes they lose their pattern, although their wind intensity is is maintaining as a tropical storm. And for the same case, in the tropical storm is classified as typhoons. This might be typhoons that have weakened into tropical storm due to landfall, or due to transitioning into an extratropical cyclones. So their wind intensity might have decreased. However, their pattern still retains those of typhoons. And lastly, these are images of typhoons that are incorrectly classified. The images of A, B, and C are misclassified as pre-storms, and the images of D, E, and F are misclassified as tropical storms. So possible reason for misclassification might be there are too many clouds that may or may not be related in the tropical cyclones present in the background. So the outline of the typhoon is obscured. So when the trained CNN model looks at these images, it might be confused since the distinct pattern of typhoons is not present, especially in this image. And this one, this is currently a typhoon in wind intensity. However, since it is already in high latitude and it is currently in landfall, its wind intensity is currently classified as typhoon. However, the pattern is already deteriorated. And same with the typhoon images misclassified as tropical storms. They might be typhoons that are starting to weaken into tropical storms. And now, for the quantitative evaluation, we have the precision, recall, and F1 score of the cyclone categories. So in the precision, the highest one is the typhoons, with the lowest in the pre-storms. So for the precision, when the model tries to categorize something as typhoon, tries to categorize a tropical cyclones on the typhoon categories, it is most likely correct in the typhoon class compared to the pre-storm type. So for the recall, the highest is the pre-storms, with the lowest being the tropical storm. So for this one, if you remember, there are high rate of misclassifications of tropical storms into a pre-storms. So this affected the recall score of the tropical storm category. And the F1 score of these categories, the lowest one is the tropical storms. The second is the pre-storms, and the highest has the typhoon pattern type category. The average precision across the three classes is 0.733, while the average recall is 0.716. And lastly, the average F1 score across all classes is 0.714. So score of 0.1, an F1 score of 0.714 is considered good in image classification task. And now, we are finished in the tropical cyclone classification results. We will now discuss the results in the tropical cyclone detection. So this figure shows the accuracy and the RMSE plot in the training process of the faster RCNN detector. Immediately, we will notice that at the start of the training, it is already hovering around 100% training and validation accuracy. This is because it carried over the learning progress of the previous task. So since it already learned how to classify tropical cyclones, it is now only focused on detecting and approximating the location of the tropical cyclone in the image. So this is the summary for the training result. The training lasted at around 23 hours with the training and validation accuracy at around 100% and the training and validation loss of 0.1. And this, after the training of the detector, we will proceed on running it on the test set of the detection dataset. So these are the satellite images of Western Pacific Basin with detected tropical cyclones. So this is the result of those detector. So for the colored magenta are pre-storms, and the colored green are detected tropical storms, and the colored cyan are detected typhoons. So this is like the final result for the detection of tropical cyclones. And now in the previous one are images, and this one is in a video format. So the red boxes are the predicted bounding boxes, while the black are the ground truth. So the black boxes, these are the actual tropical cyclones with their labeled categories. So this in video format, it resembles those of if you have seen motion detector. So the detector that I have trained closely follows the those of the ground truth. So to get a closer look, pausing the video. So for this one, although in this instance, the predicted tropical cyclone, its location is correct. However, the category is incorrect. So for this one, the actual wind intensity of the tropical cyclone is a tropical storm. So it is a typhoon that have already weakened. However, since there are, for the features of a typhoon, there might be something resembling an eye. So it might have mistook it for a typhoon. So for this one, this is a correct detection. So the bounding box, although not as large as the ground truth label, the ground truth label is subjective because it is using the Dvorak technique. However, the classification, the wind intensity classification is correct. So this is a tropical storm, and the detector detected a tropical storm. And now, this table shows the summary for the faster RCNN detection results. So for the PST, for the ground truth label, there are 132 total ground truth bounding boxes. The detector predicted 165 pre-storms. However, there are only 26 correct detections. For the tropical storms, there are 446 labeled. There are 446 labeled tropical storms. And the detector predicted 469 tropical storms, and there are 194 correct predictions. And for the typhoon class, we have 411 actual typhoons. The detector predicted 383 typhoons, and the correct number of predictions is 290. So immediately, we will notice that there, as the wind intensity of tropical cyclones increases, there are more and more correct detections. So looking at the precision recall curve, so for this one, for this figure, ideally, we want a high precision as the recall rate increases. So in an ideal scenario, this is just a solid rectangle. So that means that type of graph, a box from 1 to 1, is a 100% correct detection rate. However, we can see that the detector performed worse on a pre-storm class. And there's a middling performance in the tropical storm class, and it performed pretty well in the typhoon pattern type class. So numerically expressing the precision recall curve, the average precision for the pre-storm type is 0.04, evident from the low scores that we can see on the graph. For the tropical storms, we have 0.205, and the score for the typhoon class or the typhoon pattern type is 0.656. So the mean average precision across all these classes is 0.300. So meaning when you present it with a with a satellite image containing tropical cyclones, there is a 30% chance that it will detect that tropical cyclone and along with its correct wind intensity category. So with those results, we can conclude that by splitting the task, this is the classification task and the detection task, it is possible to train a machine learning model using a decent device. Second, it is also possible to reliably identify tropical cyclones based on their Dvorak cloud patterns using a convolutional neural network. And lastly, we can conclude that stronger tropical cyclones are easier to detect than weaker ones, evident from the low detection score of pre-storm and a high detection score of typhoon pattern types. As for the recommendations, I recommend that separating the tropical cyclones into more intensity categories might improve its accuracy by providing it a narrower range. Second, you may, just like the study from Chen et al., you may use augmented images, but you can augment the images by changing its brightness and contrast using meteorological software like SAT-8. This might improve its feature extraction. And lastly, application of more advanced satellite-based weather prediction technique may be utilized. And before I end my presentation, I would like to first thank PAG-ASA, especially Ms. Alvin Pura, Mr. Charles Rapadas, and Ms. Maria Ana Glyza Figuracion for their mentorship regarding the Dvorak technique and tropical cyclone identification. I would also like to acknowledge the website of Data Integration and Analysis System, or DIAS, for providing satellite observations. This paper would not be possible without the guidance and resources that they have provided. And with that, I end my presentation. Thank you for listening. The floor is now open for questions and for clarifications that you might have. Thank you.